Here's another example of LS coupling, aka RS coupling, aka Russell-Sunders coupling. It only works for a particular class of situations. I'll tell you later what they are. So let's do it over here because I want to leave the result up on the board after we finish it. So let's consider carbon. This is an excited electron configuration of carbon. Ground would be 2p2 and that's it. So I've got a reason for doing this. So I could put ones here, but you understand the one. Now one thing you need to know is that filled subshells make no contribution to the term symbol. Okay? That's the short, I needed to tell you that. So there's a longer reason though. You may remember back when we were talking about orbitals, I told you that if you fill up a p subshell, the net angular momentum is 0. If you fill up an s subshell, the net angular momentum is going to be 0. Also, all of the electrons are paired. So the net orbital angular momentum is 0. I put a capital because it's the total orbital angular momentum, but it's only for those subshells. It's not for the whole. I'll put a prime in here just to make you, it's just for the subshell. Because all the electrons are paired, capital S is 0, and therefore, of course, J prime is also 0. So we can ignore them when we calculate the terms. Okay. So all we have to think about are these. So let's proceed. I'll just sort of circle that, put it up there. So we have 2 electrons. They're both in p orbitals, so little l is going to be 1, because that's always true for a p electron. And little l then is, little L2 is also 1. That's the little strange noise. Of course, little s is always a half, that's all it can be. So I'll first think about L, and remember I'm going to use the Clebsch-Gordon series, so it goes from a maximum of that's the largest it can be, all the way down to that absolute value. And you can see this is 1 plus 1, which is 2. This is 1 minus 1, which is 0. Now we go down by units of 1 from here, so we have 1 in the middle. That's all we got. So we've got 2, 1, or 0. 2 possibilities for capital L. Capital S. Now, a half plus a half is 1, a half minus a half is 0. If we subtract 1 from 1, we just already get to 0, so that's all we've got. Okay. So we got capital L, we got capital S. For each combination of L and S, we need to determine capital J. So I make a table. Now, in principle, each capital L can go with each capital S. Okay? So 2, 1, and 0 can be coupled with this 1 or with this 0. So that gives us, 6 possibilities. This looks very much like what we did, the example we did last on Monday. So now we couple these, and again we use the Clebsch-Gordon series. So we're going to start with, so J can be L plus S all the way down to the absolute value of L minus S. And this is going to be 3. Maybe I should make that bigger. 2 minus 1 is 1, so we have a 2 in the middle. So we can have 3, 2, or 1. And let's make these a little farther apart. Okay, so the next possibility is 0, 2, and 0. L plus S is 2, L minus S is also 2. So 2 is the only possibility we've got. 1, 1. Now I'm just going to do it in my head. It's the same process, but I'm not going to go through all the details. 1 plus 1 is 2, 1 minus 1 is 0, there's a 1 in between. 1 and 0, 1 plus 0 is 1, 1 minus 0 is also 1, that's all we got. Uh, 0 plus 1 is 1, 0 minus 1 is negative 1, whose absolute value is 1, that's what we got. And 0, 0, just give me 0. That's it. Now let's figure out the term symbols, and to keep it looking a little neater, let's use a different color. So this is a L equals 2 term, so L equals 2 corresponds to capital P. Remember, it's just like if little l is equal to 2, we have a p orbital. If capital L is equal to 2, we have a capital P term. So the nomenclature for the terms is just like the nomenclature for the orbitals. Then we need the multiplicity m, which is going to be 3. Remember, m, the multiplicity is 2s plus 1. S is 1, 2 times 1 is 1, plus is 2, plus 1 is 3. So this is a set of triplet P terms. We have 3 of them. One is for j equals 3, another is for j equals 2, another is for j equals 1. Now I've combined the terms just to be compact. What this really represents, how should I do this? We really have 3 terms. I wrote them like this to be compact, which you'll often see done. Okay, but it's really 3 terms. These are the 3 possible values of j. Any questions? Yeah.
Is it not D for L equals 2?
Oh my gosh, yeah. That's a D term. I think I did the same thing with F. L equals 2, these are, the little l equals 2 orbital is a D orbital, capital L equals 2 is a D term. And so these are, thank you. Please, I make mistakes now that I'm talking and I just get too much going on for me or something. So that is correct. Okay. So down here, this is another, if we go to that second row, L equals 2, so again it's a D term. S equals 0, so the spin multiplicity is 1, twice 0 plus 1. And we only have one possible value for j, that's 2. That's just that term. Going in down here, capital L equals 1 is a capital P term. S is 1, it's a triplet P term. And 3 possible values for j, so I'll combine my terms to be compact. Here, we've got, again, L equal 1, capital L, so this is a P term. S equals 0, so it's a singlet, and L is 1. Then down here we have capital L 0, so this is an S term, but it's a triplet because S is 1 and J is 1. Triplet S term for J equals 1, and lastly, L is 0, so we have an S term, S is 0, so it's a singlet S term, and then J has to be 0. Notice, by the way, that anytime capital L and capital S are both 0, they're going to have a singlet S term. So if you were to calculate, if you were to write the term symbol just for the subshells, you really shouldn't, but it would be singlet S, 0. Questions? So do some practice, and I don't think I'll pull up the worksheet quite yet, because I'll be too much up and downing, but I'll show it to you in a second. Those are the basics. I now want to introduce some kind of new ideas, or I should say they're kind of subtleties. And I'm going to do that by calculating with LS coupling a particular helium excited state we've already looked at, and comparing that to the helium ground state. So the helium excited state I want to look at I'll put the ones in just to remind us you don't need them. Okay. We looked at that before when we talked about singlet versus triplet. So let's use LS coupling now. Well, the little l's are both 0 because these are s orbitals. So capital L can only be 0. That's just like we had over here, so I don't need to do any work. Okay. So we have two possible values of J. So we have L0, if S is 1, J is 1. If F is 0, J is 0. So this is an S term, capital S, because capital L is 0. It's a triplet. There you go. And this is also an S term. It's a singlet. You've got these two different terms that arise. Okay, fine. I'm going to compare this with a couple of things. First thing I want to do is compare with the idea of triplet and singlet that we talked about a while ago. If you recall, I said the total wave function depends on two electrons. I'll call them 1 and 2. And it has a spin part and it has a spatial part. So I said, let's take this apart. And I said the spatial part, there are a couple of them. One we called psi plus. And of course, the overall wave function that includes spin has to be antisymmetric with respect to the interchange of two electrons. This spatial part is symmetric, so it had to be coupled with an antisymmetric function, which we called sigma minus. And just to remind you, sigma help. It's this combination, linear combination of an alpha times a beta, alpha 1 beta 2 minus alpha 2 beta 1. Okay. we saw that before. That's this. Then the other possible spin function now this spin function is antisymmetric with respect to the interchange of two electrons. So it has to be coupled, the spatial function is. So the spatial function has to be coupled with a symmetric spin function. And there are three possibilities. Alpha alpha, beta beta, and sigma plus. And let me remind you what sigma plus is. It's the same as sigma minus, but there's a plus sign here. So that's kind of interesting. Well, let's think about this for a second. Think about this with respect to this stuff. If both electrons are pointed up, 1/2, then we're going to have a total spin quantum number of 1. If both electrons are pointed down, we have a total spin quantum number of 1. And what about this? Well, there's another quantum number that we can think about. If S is equal to 1, that's the total spin quantum number. That total spin can be pointing up, horizontally, or down. So if it's up, we have capital M sub capital S equal +1. This is the Z component of the total spin angular momentum. Yes?
I'm confused on the, where you have 1/V2.
Huh?
What does the V represent?
What does the, I'm sorry, I didn't.
Was that a square root or?
Yeah, this is a square root.
Oh, okay, sorry.
Sorry. Yeah, this out in front is a normalization constant. Yeah. So this total spin angular momentum can have a +1 Z component. It's really +1 H bar, but the quantum number M sub S can be +1, 0, or -1. Okay. Now the reason, if you think what's going on with the +1, it's because we have one electron up and the other electron also up. And that's 1/2 plus 1/2 gives you 1. Or they can both be down. -1/2 minus 1/2 gives you a -1. But it can also be horizontal. And that's when the electrons are pointed in opposite directions. And that's really what the psi plus is about. And this was our triplet state. Okay. So notice that the term symbol we came up with did not specify all the states exactly. You'd also have to specify M sub S, capital M sub capital S. Notice that all three of these derive from the triplet S term. This, on the other hand, derives from the singlet S term. So you were probably confused or wondered what was behind this plussing, this minusing, or I should say, what's behind these two different things? Both seem to have an alpha and a beta, one up and one down. The difference is, in one case you have total spin angular momentum 1, and the other total spin angular momentum 0. So they're actually different in different energies and everything. In fact, it's interesting to look at the cone model representations of these. So let me show you those. Yes.
So there's no possibility for the anti-symmetric spin function to have both of them in the same direction?
Correct. Correct, yeah. And we'll come back to that. So what I'm trying to do now is help you to connect in your mind different visual representations and mathematical representations of these different states of charge. That's what I'm trying to help you with. So we're looking at this right now. So here's a cone model that represents here, these two right here, the possibilities. I didn't put everything down, but if capital S is 1, then if m sub x is +1, you're like this, -1, you're like this, and 0, you're like this. Okay, you got 3 orientations. For the capital S equals 0 term, it's kind of like this. And the only way to really make sense of this with these diagrams that combine cones and vectors is to have this one pointing not only down, but in this direction, and that one up in the opposite direction, because then the vectors truly do sum to 0. Just thinking the way that, visually vectors sum. Here, you notice you have to have the x and y components being the same in every case. And then you'll have a z component that's 0, but the total angular momentum is still 1. Every representation has its limits. It will start to tell you lies if you push it too far. That's a problem. Now I want to come back to orbital diagrams and prove to you that they have limitations. So suppose I wanted to represent alpha alpha. Well, that would be easy, right? That would be alpha alpha. Suppose I wanted to represent beta beta, that would be easy. Suppose I wanted to represent psi plus. Well, that's made from 1 up and 1 down, right? It doesn't matter which one's up and which one's down, it could be like that. So this could be alpha. That could be alpha plus. Okay. But what if I wanted to represent alpha minus, sigma minus? It's 1 up and 1 down, right? But the orbital representation is the same. So the orbital diagrams only go so far, they can't tell you the whole truth. So they're very valuable, but you can only push them so far. Okay. Questions? So let's compare this now with another configuration. This is the ground configuration. Notice I did not say ground state, because there might be several states that correspond to the same electron configuration. So I called this the ground configuration. What happens if we try to figure out the term symbol and we apply the same method, LS coupling? Well, I'm actually getting the same answer I got up here, because both little l's are 0, both s's are 1/2, and so I'm going to get exactly the same answer as I got up here, right? So I'm just going to write same as above, right? In other words, I'm going to get a triplet S and a single S. Let's write orbital filling diagrams that correspond to the triplet S. Here's the 1S. There will be several of them. One of them is going to have 1 up and 1 down. Okay. In fact, there's going to be another 1 up and 1 down. One corresponds to sigma plus, one corresponds to sigma minus. And then the first one will be both up and both down. LS coupling would say you can have all of these. Are there any problems? Nobody see a problem here? Yeah, the Pauli exclusion principle says that into one orbital you can only put 2 electrons and they must be paired. Okay. So that's no good, right? You can't have 2 up electrons in one orbital. You can't have 2 down electrons in one orbital. Those are obviously, they contradict the Pauli exclusion principle. So anytime, in fact, that we have more than 1 electron in a given orbital, a given unfilled orbital, not or partially filled orbital, you can't use LS coupling. That will predict the wrong results. It will overcount the possible terms. So this is the bad news. I haven't given you a tool to deal with the situation. There are tools. You make these little boxes with little matrices, basically, and you count possibilities. I'm not going to teach that to you because it's a bit, we have better things to do with our time. You can easily learn it. So if you ever deal with this kind of stuff in detail, you'll have to go learn that yourself. You can read online and find out how to do that. Okay. So these are excluded by the Pauli exclusion principle. It turns out that this one is also not possible. Although it looks visually like it's 1 up, 1 down, sigma plus is not possible. Only the sigma minus is possible. So when we use the word the term paired electrons, that doesn't mean 1 up, just that means more than 1 up and 1 down. It means sigma minus. Okay, you can't have 2 electrons described by a sigma plus, 2 electrons described by a sigma plus in the same orbital. You can't have that. Okay. So paired electrons, just remember, means more than 1 up, 1 down. It has even a deeper meaning. Questions?
So you can't have the sigma plus because it includes the 2 alpha, beta terms?
The reason you can't have the sigma plus is that, remember, we have to construct our wave function that includes spin. And there's going to be a spatial part times some spin part, right? And the total thing must be antisymmetric. Now, what is the spatial part going to be? It's going to be 1s1, 1s2. And that's really a sigma plot. That's really a symmetric combination. There's no way to make an antisymmetric combination. So the spatial function will have to be symmetric if it's the same orbital for both electrons. Therefore, we need the antisymmetric spin function, and it's got to be sigma minus. It can't be sigma plus. Okay.
So ground state, the wave function has to be symmetric, and then the electrons themselves have to be antisymmetric.
Yeah. Yeah. Questions? Another caveat, we're dealing with the subtleties, right? Just the subtleties. It turns out, suppose you've got a p orbital. You can put 1, 2, 3, 4. You can have P1. You can have 2 electrons in the P. You can have 3 electrons in the P. You can have S all the way up to 6, right? You can have an S orbital. You can have 1. You can have 2. Anytime you have more than 1 electron in a partially filled orbital, we call those electrons equivalent. Okay. These are also equivalent, actually. So when you have equivalent electrons, you cannot use LS coupling. one exception. Suppose you have a subshell that is almost filled. It's filled, but it's missing one electron. That would be a P5, it could be a D9, because you can put 10 electrons in a D subshell. So if you have 9, you're missing one electron. It turns out that the rules for figuring out the term for P5 are the same as for P1. D9 is the same for D1. That seems funny. Think about it this way. Suppose I had a D6. What's the total spin quantum number for a D6 orbital? Completely filled orbital. D6, electrons are filled, every orbital is filled, every orbital has an up and a down, and that is 0. The capital S, just for that filled orbital, is going to be 0. Now suppose that I take away one electron. I've removed S being 1/2. I'm left with 1/2, right? So if you subtract one electron from a filled orbital, capital S will be 1/2, which is the same as if you had one electron. So this will be capital S of 1/2. That would be capital S of 1/2. And so anytime you have an orbital that is completely just missing one electron, you can still use LS coupling. Treat it as if it were one electron. Okay. So that's kind of a sidebar thing, but it's true. I think I've said all this. I think I wanted to say about subtleties. Any questions? So you can deal with a lot of stuff. You've learned how to apply LS coupling. You know you can't apply it when there are equivalent electrons, unless it's a subshell that's filled, except for it's just missing one electron, and you can still deal with it. You learn what equivalent electrons are. Yeah, I think those are the basic ideas. Okay. And you've also, I want to come back to this. I want you to appreciate that many of our visual tools are helpful, but they have their limits. So the orbital diagrams tell us a lot, but they don't tell us everything. So I think then I want to go to this. Maybe first of all, since I promised I would, I'll show you these worksheets. So there's one on coupling angular momentum. I'll show you what it does. Maybe. Okay, I've learned not to wait forever. Just download it. Okay, the top of it just tells you about LS coupling. You're asked about good and bad quantum numbers, which I'll review today. We've talked about them. Then you get a couple of examples. This is taking you through the coupling, for 2p1, 3d1, or 3p1, 3d1. Calculate. Oh, man. Thank you. Okay. So you're asked about quantum numbers, good ones and bad ones. See if you can remember what that means. You're giving some practice with calculating capital L and capital S. Okay, this is just talks about capital M sub L and capital M sub S, which is good to think about. We'll talk about JJ coupling later today. So that is this particular worksheet, which is due for no credit later. And then there's another one. Where did it go? There's actually a separate one on term symbols, but term symbols aren't hard if you understand what also side is going to be. Oh, and then at the bottom, we talked about spectroscopy, which, oops, we're gonna talk about later today. So leaving that alone, let's go back to here. I guess we talked about one here. We talked about any filled subshell was just, you can ignore it. What if you have 3 electrons to worry about? If they're equivalent, you can't deal with them, but if they're different subshells, couple one to another one to get a capital L and a capital S just for those two, and then couple those two to the third. Step by step. Okay. Now, suppose you've calculated a number of terms, and you wonder, can you predict which one is higher, which one is lower in energy? And the answer is we can. We can if the electron configuration is the ground configuration. Then we've got this set of rules. If the electron configuration is a little higher in energy than the ground configuration, the rules won't always work. They work pretty well for low energy excited configurations and progressively less well as you go higher in energy. So they're worth kind of working with, but don't overuse them. Here are the rules. You apply rule 1 first, and then you only apply rule 2 if rule 1 doesn't leave you with an answer. And 3, only if rules 1 and 2 don't leave you with an answer. For first, the greatest multiplicity has the lowest energy. Triplet is lower energy than singlet. What if you have 2 triplets or 2 singlets or something? Then you go to rule 2. For a given multiplicity, the term with the largest L has the lowest energy. Now, let's just leave it. I'll talk about the rules first, what they are, and then I'll give you a notion for why they might be what they are. So that's pretty not so hard. So if we look at these, by the way, over here, which we calculated for a particular excited configuration of carbon, right? Now, since it was an excited configuration, the rules are not going to apply perfectly. Well, let's hypothesize that they'll apply pretty well and see what they would predict. Well, we have 2 triplet terms and 3 singlet terms. Well, we have several G's as well, but the triplets will be lowest in energy. And between these 2 triplets, we choose the one with the largest value of L, which is that, D or P. Capital D corresponds to L equals 2. Capital P corresponds to L equals 1. So the lowest energies for the higher L. So we predict that would be the lowest, the 3D, followed by the 3P. So that's how that works. Among the singlet terms, we predict the 1D lower than the 1P lower than the 1S. The last rule is a little more complicated. What if the multiplicity and the L happen to be the same? So we're talking about like this set of terms, the 3D3 versus the 3D2 versus the 3D1. Now it gets more complicated. We first have to ask ourselves, is the subshell more or less than half filled? Now that's only going to make sense if you're talking about only one partially filled subshell. If you have 2, it's not obvious what it works, but let's suppose it's going to work that way. Both of those are less than half filled. The 2P and the 3P are both less than half filled. If we assume it's going to work, it says, if the subshell is less than half filled, the term with the smallest J has the lowest energy. So the 3D1 would be lowest, and then the 3D2 would be 3D3. But if the subshell is more than half filled, the term with largest J has the lowest energy. So it's a little complicated. I wouldn't sweat it too much, but try to apply the logic now and then. Now, why might this be? The multiplicity rule, we already saw before that a triplet was lower in energy than a singlet. That was because of spin correlation. Spin correlation is this pretty abstract notion But now you can see why it's one reason it might be important. What about 2? The way that people, that makes sense, talk about this. It's electrostatic. We know if 2 electrons are close to each other, that's bad. They repel, that's high energy, right? Well, if 2 electrons have the same are traveling in the same direction, they can stay far apart from each other. So they could both be in the same orbital and still stay solid far apart. So in other words, they would have the same M sub L values, and the M sub L's would add up and give a large number. If they're traveling in, I can do this. If they're traveling in opposite ways, they're going to meet every so often, get close to each other every so often. That would correspond to a plus M sub L and a minus M sub L, right? So in other words, low capital L. So the low capital L's to be, that's your, yeah. Read your book for the justification. It's there, it makes some sense, but it's too weedy. Okay. So, I think the example I might give will be based on this slide. I showed you this slide the other day. I've made it a little easier to read. So these are the energy levels for carbon atom terms resulting from those 3 configurations. In the top configuration, notice we have 2 equivalent electrons, the P2 term.
Yes.
So LS coupling is not going to work there, by the way, if we want to predict the terms. Then we have 2 different excited terms. So these are the ones that come out of the ground configuration. And if you applied LS coupling, you get more than this. But these are the ones. Notice, let's see if these rules work. Notice the triplet is lower in energy than the singlets. That was supposed to be the case. And between the 2 singlets, the one with the larger value of capital L is lower in energy. Those were the first 2 rules. So it kind of worked. They didn't try to separate out these. They were very close in energy, probably not exactly the same. And then upstairs, we can see whether our predictions, our calculations were correct. We predicted triplet D terms. There's a triplet D, 3, 2, 1. So that's this guy. We predicted a singlet D term right there. We predicted a triplet S right there. We predicted a singlet S right there, a triplet P term, and a singlet P term. Okay, so we got them all. Yay. You'll notice that the ordering is kind of like what the rules predict, but not exactly. Notice the singlet D is lower than the triplet D. That breaks the rule.
Yes.
Right. That's a deep question. I'm not going to try to answer. Okay. Yeah, and you can see the rest. Okay. Okay. So we've learned how to approximately order the energies in terms. And we know it doesn't always work. It works for the ground configuration. Let's talk about spectroscopy. I'm going to go back up. Okay. If you shine light on an atom, the atom in principle can absorb some of the light. And if the atom absorbs the light, then the state of the atom will have to change. So, for example, you might make a transition from, well, none of these is going to work, is it? In principle, you might think you can have this transition, and that difference in energy would correspond to a photon of some wavelength. So you get a spectrum.
Yes.
That's fine, as far as it goes. There are, however, spectroscopic, there are selection rules. So not every possible transition is actually observed if you take a spectrum. And these are the selection rules. I can justify some of them for you, not all of them, easily. Capital S is 0. Okay. So you don't change, so the value of S cannot change. Okay, let me back up a moment. That means we can't go from here to here. Remember, this is a triplet, so for it, 3P, M equals 3 because S is equal to 1. Up here, M is equal to 1 because S is equal to 0. S can't change according to the selection rule. You won't observe that transition spectroscopically. There may be other ways to go from here to here, but not by absorbing a photon of light. Next rule, I guess I should say the way that, well, if there's strong spin orbit coupling, that might be observed. That selection rule actually can be broken, but spin orbit coupling is generally pretty small. So capital L has to be 0 or plus or minus 1. Why is that? If a photon of light is absorbed, one of the little L's has to change, either by plus 1 or minus 1. And if one of the little L's changes, capital L can change both plus or minus 1. It actually might not change at all, depending on the orientation of that little L. And then the third spectroscopic rule is that delta J can be 0 or plus 1 or minus 1. However, J equals 0 cannot go to J equals 0. That's what this symbol means. You can go from J equals 1 to J equals 1. You can go from J equals 2 to J equals 2, or J equals 2 to J equals 3. You can't go from J equals 0 to J equals 0. This is forbidden. So let's apply those rules for fun.
No reason why it's forbidden?
Sorry?
No reason for why it's forbidden?
So, I'll say some gobbledygook. There's something called as a spin. The origin of the selection rules is an integral, and it's called the transition dipole moment. We will talk about the transition dipole moment as an integral when we come to spectroscopy. Often, one can identify a simple physical principle that causes the transition dipole moment to be equal to 0. If the transition dipole moment is 0, the transition does not happen. Often there's a simple physical principle. I identified one for delta S, but I can't often identify it as a simple physical principle, so I'm just going to try. But it does come down to the value of that integral, which I have to put off. Okay. I'm sorry. I know, but we'll come to it. Okay, so let's try applying those rules. Well, I can't make this bigger, but I can go to here and make this bigger. There. So I'm trying to think how I'll manage this for you guys. I can't manage it so everybody can see anything, but let's just think about the terms around 7,000, the ones that arise from just one configuration. So let me write it down. There's a 1D2. Yeah. 3D321. Oh, let's not do it that way. So let's apply the rules. Let's think about the 1D2. What transitions which of those states could it go from? Or could it transition between the 1D2? So yeah, so potentially it could go to, I think there's only one it can go to, that's the 1P1, right? It can't, it's a singlet, it can't go to any of the triplets. in capital D, remember, capital L can be 0 or plus or minus 1. Capital D is 2.
S is
Capital S is 1, so it can't go to a capital S. So that just leaves the P terms. So it's got to go to the singlet P1. Now, how do we write this? I want to show you how we write a transition. So which is higher in energy? P is, right? So 1P, what goes down here? I can't see it. 1, okay. And the lower term is the 1D2, right?
Yep.
So the convention is to write the higher energy term on the left. Therefore, if we're talking about absorption, we write a left arrow. We're going from the lower energy to the higher energy term. That's absorption of light. What if we're talking about emission of light? So you're in the higher energy term, you can emit a photon, and then the atom will fall to the lower energy. So emission So, as we write this, absorption will always be written with the left arrow because the higher energy term is written on the left. And emission will always be written with a right arrow. Okay. So either of these two is allowed. I'm going to write all the possibilities as absorptions for right now. Can I erase this? Or you guys can't even see anything. Okay. Okay. So that's one possibility is absorption. What else do we have? What about the singlet S to the singlet P? Is that allowed? Right, so delta capital S is 0. That's allowed. Delta capital P is -1. Delta capital L is -1. That's allowed. And what about J? Delta J is -1. That's also allowed. So we can do that. 1 is 0, 1 be 1. Okay, so that's fine. I think the only other possibilities would involve the triplet terms. There are 3 of them. The S and the D, that's a forbidden transition. Why?
The L is 2, the difference.
Delta L is 2. Right. For S, L is 0. For D, L is 2. So delta L is 2. That's no good. But the S can interact. One can have a spectroscopic transition between S and P, or between D and P. Those are the 2 possibilities. So, S. No, that's no good. That would be good. And triplet P with the D. Okay. We're running out of time, so I won't deal with the J values, but only particular J transitions are allowed for the J values, because delta J is, you see the rules. So there are a couple more details here, but I'm going to stop with this. Let me, oh gosh, we're over time. Sorry about that. Okay. I'm gonna, what do I want to do? Let me tell you this overview. This brings together what we've learned about term symbols and about splittings. We have a summary of interactions responsible for splitting. The configuration doesn't tell the whole story, right? One is the orbital occupation. So those are the little L's, little L1 to little L2, you know. They will sum to give a capital L. And that can lead to splitting. The reason that the little L's interact is electrostatic. Are the electrons close on average or far on average from each other? So when we couple little L's, we get the letter part of the terms of the term. Then there's also spin correlation, which depends on the spin part of the spin correlation is there's a spin, there's a spatial part. And that will give us then a dependence on the spin, total spin quantum number, how the spins add up. And lastly, there's the magnetic interaction, which is the spin-orbit interaction. As I said, Russell's Saunders-Summers coupling works in some instances, not in others. I will come back to this with like one remark on Friday, and then we'll start chapter 4 on Friday. That will be it'll be molecular structure of the molecules. Sorry for keeping you late. We had a kind of rough start. Have a good day.